Chapter 10, Section 3, Theory and Computation of Orthogonal Projection. In the previous lectures, we studied the definition of orthogonal vectors, projection onto a single vector, and projection onto a subspace using an orthogonal basis. In this lecture, we will further deepen our theoretical understanding by explaining the precise definition of projection and mathematical properties that projections satisfy. Let us begin by clearly defining the fundamental meaning of the projection operation. Let W, a subspace of a vector space V, be a subset of V. For any vector B in V, the orthogonal projection of B onto W, denoted as P in W, is defined as the unique vector that satisfies the following condition. B minus P is orthogonal to W. That is, the inner product of B minus P and W equals 0 for all small w in large W. Here, the inner product refers to the dot product of vectors. This equation means that the difference vector B minus P is orthogonal to any vector small w in large W. It implies that P is the point on W that is closest to B. Suppose the subspace W is spanned by k vectors u1, u2, uk, and that these vectors are mutually orthogonal. In this case, the orthogonal projection of any vector B in a vector space V onto the subspace W is given by this formula. So, why does this formula yield a correct projection? The key lies in the relationship between orthogonality of vectors and a vector decomposition into components. We can explain the reason by three key points. First, projection measures the component in each direction. Component represents contribution. Second, orthogonal vectors point in mutually independent directions and do not interfere. Third, adding the projections reconstructs the component of B that belongs to W. Let's explore each point one by one. The first point is that projection measures the component in each direction. The projection of B onto UI calculates how much the vector B overlaps with the basis vector UI in direction. That is, how much of B's content is aligned with UI, or, in other words, how much B contributes in that direction. For example, if part of B is aligned with U1, the projection extracts that aligned shadow. This operation corresponds to measuring the vector B along each direction. Orthogonal vectors point in mutually independent directions and do not interfere. Orthogonal vectors span completely different axes in space. Because they are mutually orthogonal, the component of B in one direction does not interfere with or affect the computation of components in other directions. This means that each basis vector contributes independently. In other words, just as horizontal and vertical directions are independent, orthogonal vectors point in non-overlapping directions. So, there's no duplication or confusion of information. The third point is that adding the projections reconstructs the component of B that belongs to W. By projecting B onto each orthogonal basis vector UI, we can determine how much of B lies in each of those directions. Since these directions are orthogonal, the components do not mix, that is, they are independent. And we can accurately extract only the parts of B that belongs to the subspace W. By summing all these projection vectors across different directions, we can reconstruct a part of B that belongs to W. Next, we will explain three fundamental properties of orthogonal projection: idempotence, orthogonality, and linearity. These properties play a central role in various applications of linear algebra, especially in regression analysis and principal component analysis. First, let me explain idempotence. Orthogonal projection is an operation that only needs to be applied once. Applying it multiple times yields the same result. This means that if the vector P is the orthogonal projection of B onto the subspace W, then projecting P onto W again will not change it. The result is still P. In linear algebraic terms, this implies that the projection matrix is idempotent, that is, P to the power of 2 equals P. Let me give you an intuitive example. Imagine that vector B is an arrow pointing from the origin to a point floating above the ground, and the subspace W is the floor. Then, P is the projection of B onto the floor, like a shadow of the arrow falling straight down onto the subspace W, landing at the closest point on W. If you try to project P again onto W, nothing changes. It is already lying in the subspace. Just like casting a shadow of a shadow, it stays exactly where it is. The difference between the original vector B and its projection onto W, that is, the residual vector, is always orthogonal to the subspace. Geometrically, this means that the projection is the point on W closest to B, found by dropping a perpendicular from B to W. This orthogonality property plays a crucial role in optimization problems. A more detailed explanation will be provided in later chapters. Orthogonal projection is a type of linear transformation. This means it satisfies the following two key properties. Additivity. Projecting the sum of two vectors is the same as the projecting each one and then adding them. Homogeneity. Scaling a vector before projecting gives the same result as projecting first and then scaling. These properties are expressed in the following equation. Because of this linearity, projections can be represented using a projection matrix. Representing projection as a matrix means you can compute it efficiently. It can be easily implemented in code. It fits neatly into the framework of linear algebra. For example, in linear regression, the projection matrix P is given in this way. Here, X is the design matrix that includes the explanatory variables. Y is the vector of observed values for the responsive variable. Using this matrix, we can compute the predicted values y hat by projecting y onto the model space. This gives us the best linear approximation of y in terms of the variables in X. Orthogonal projection is not merely a shadow of a vector, but a well-defined mathematical operation with powerful structural properties. These properties make it indispensable in both theoretical mathematics and real-world data analysis. Thank you for watching. Please thumbs up and subscribe to my channel.